Here we're going to take a look at a very typical fundamental theorem of calculus type of problem that we see a lot of times on the AP exam. Okay, so we're going to have some questions here asking us about function g. And function g is defined as the definite integral from -4 to x of f of t dt. So to answer any questions about function g, we're going to have to use the graph that's given to us, which is the graph of function f. Okay. Now, just to talk relationships here, if I want to answer anything about whether function g is increasing, decreasing, or critical points, we know we use the first derivative of function g. Now, this is where the fundamental theorem of calculus comes into play. The derivative of the right side of this would simply be f of x. Now, if I'm asked any questions about concavity, then I'll be using f prime of x, and we know f prime of x is slopes. So we'll be using the slopes of the given function f. Okay, let's answer several questions here. Part A. G is the function defined. We already discussed that. What is find g of -1? Okay, so function g of -1. Then we're going to look at the definite integral from -4 to -1, which now in this situation we'll use area. So from -4, 1, 2, 3, 4, to -1 is this area. Here we have a trapezoid. So the base on the left side, 2, 3 is 3. Base on the right side is 2. The height is 3 units. So by using the formula for the area of a trapezoid, we know it's going to be negative. So we have 5 times 3 gives us 15 halves. Okay, in the next part, it wants us to find g prime of -1. So g prime of -1 is going to be equal to f of -1. Okay, in this situation, I'm just going to look at the graph, locate f of -1. So this is function f. -1 is right there. So we know that value is equivalent then to -2. In the last part, g double prime of -1. G double prime of -1 then is equal to f prime of -1. And then, again, look at the graph, locate -1. What is the slope at -1? Well, the slope of f does not exist. We got a sharp turn there. It does go from decreasing to decreasing, so it's not going to be any type of critical point either. So that is part A. In part B, for function g defined in part A, find the x-coordinate of each point of inflection of the graph of g in the open interval from -4 to 3. Okay, so we're talking inflection points. So that means we're going to be looking at the second derivative of g, which for what the information we're given of f, we'll be looking at f prime. I want to know where does this equal 0, or where does it not exist? So f prime, we're referring to the slopes of f. So let's scroll up here to our graph. Okay, and well, we have a bunch of sharp turns in this graph, so we're never going to have the first derivative equal 0. But what we are going to have are some changes in concavity where the derivative does not exist. Okay, so in terms of a point of inflection, looks like our only value is going to be at x equals 1. We see at x equals 1 here, we go from having a positive slope to a negative slope. So we have a change in concavity there. Second derivative is changing from positive to negative. So at x equals 1, inflection point, okay, we have a change in concavity, concave up to concave down at x equals 1. Therefore, it's an inflection point. in part C, I want to know where does h of x, as defined as this definite integral from from lower limit x to upper limit 3, when is this going to equal 0? Okay? Now, before I even go to the graph, the most simple answer, if our limit goes from 3 to 3, meaning the limits are exact same value, that will be 0. Okay, now we're going to have to utilize area for the rest of this to figure out if there are any other values of x that would make that definite integral 0 for function f. So again, look at the integral. We're starting at, or we're ending at 3, which is this point here. So if we think about this area here, below the x-axis negative, and then this area here, which would be exactly the same area in value, 1 negative, 1 positive, that would be 0. So if the definite integral went from 1 to 3. So 1 is our second answer. Okay, now, again, let's see. We have this area. We add those 3 areas together. Again, the top is positive. The 2 below the x-axis are negative. Those would add to 0. So at x equals negative 1, we have a third value. This would make h equal to 0. Okay, and the last part, part D, for the function h defined in part C, find all the intervals over which h is decreasing. So in this case, h of x is defined as this definite integral. Okay, so I want to know when is that decreasing. Now normally we want to look at h prime here. Before I go ahead and take the derivative of h, this helps me visualize things a little more clearly. I'm going to look at h of x as being the negative. So my limit properties here, 3 to x, f of t dt. And now, again, I'm looking at h prime equaling negative f of x. So normally I would be looking for where the part of the graph is below the x-axis. Now in this case, since it's negative here, set negative signs there, I'm going to be looking for the part that's above the x-axis. That's when h will be less than 0. And again, that's simply because h is defined as the negative definite integral. Okay, so we go up here to the graph. Now we can visualize the graph all being reflected. Or we can just look for the part of the graph that's above. Since this is f is positive, negative f would actually make it go below the x-axis. So that's where f would be negative. So we're looking at the integral from 0, I'm sorry, the interval from 0 to 2. Reasoning, again, h prime is less than 0 for those values.